All right, thank you. And let's get started on today's session. And our first speaker is going to be Eric Blackman, who is going to be talking about connecting fundamental mean field electrodynamics to practical observations. Yep, more or less the same title.
Yes, close enough.
Thank you. Take it away.
Sure. Okay, so yes, this is a talk will have some challenges in it that are, and we'll show some of the disconnect between doing theoretical calculations and comparing to observations. And there's two components of that. One is in the context of accretion engines that I will discuss, and the other is the limited scale separation of mean field theories in these concepts. So you'll see how this sort of fits together. Lots of objects in the universe. The evidence for large scale structures, jets, is in some sense the awareness of this has been increasing in astrophysics. Objects which one thought were spherical are now largely jetted. So there's this going from a cultural sort of a perspective from seeing sort of objects like a supernova, for example, which were thought to be spherical explosions. When you look closely, they're aspherical. They also have typically jets from the engines. So this notion of the prevalence of jets, and one might interpret this as the importance of large-scale magnetic fields. In all of these cases, it's possible that the jets are driven magnetically, and that jets are a mechanism of large-scale transport. So now, and there's some evidence that the magnetic fields are, in fact, out to kiloparsec scales and even larger, still dominating the dynamics to a certain extent. Wee Lee has pointed out that jets in AGN incur bends and still retain their collimation. And how could they do that if they were hydrodynamic all the way out to very, very large distances? Now, how does this fit into the turbulence and accretion disks, et cetera? Well, we know accretion disks and the principles behind them. The need to transport angular momentum. Material falls deeper. Material falls towards a gravitating object, but can only fall as far as the if it conserves angular momentum, it falls where the speed is Keplerian, and then to fall much deeper, it has to lose angular momentum. And the paradigm for treating this in accretion disks, so Shakurins and I have recognized the macrophysical need for macrophysical transport for the angular momentum, microphysical too slow, and Balbus and Hawley introduced the MRI into astrophysics, recognizing that weakly magnetized objects would incur instability that leads to a potentially rapid transport of angular momentum, and this could solve this angular momentum transport problem. Now, it's widely assumed that the MRI amongst its users supplies a turbulent viscosity that kind of is used to support the parameterized turbulent viscosity in the Shakura-Tsarnaev model. But a question is really whether that's a local viscosity. And in fact, in accretion disk, you could have a transport from local radial transport, for example, the turbulence generated by the MRI, or you could have non-local transport, large-scale magnetic fields, for example, and also non-local vertical transport, other mechanisms as well. And so that's the broad picture, that angular momentum transport. And as we get into thinking about observations in theory, so often in the theory, which if one uses a periodic box to study in this perspective, this is a small section of an accretion disk, but we think in the big picture that accretion disks have possibly different paradigms for large-scale transport. So studying the processes within this region don't necessarily capture all of the mechanisms of transport. And if these, for example, were to dominate, what's the connection between this box here and learning about these larger scale mechanisms of transport? So, so this is sort of when people use, so there's a disconnect between the simulations of accretion disk and turbulence and what modelers of accretion disk spectra actually do. So what modelers do is to take a Shakura-Tsarnaev multicolor black body model, assuming that the transport is a viscous transport and local, produce the thermal sort of spectrum, and then pop onto that by hand in a linear combination some amount of a hot corona where X-rays are produced, and possibly a jet as well. And then by dialing calculate a spectra for material at a certain temperature emitting X-rays, and you dial that in the right fraction by hand and match it to the disk spectrum and tune those by hand to create an overall spectrum that's the sum of these different components, a coronal component, a disk component, and then a reflection component. The corona reflects onto the black hole. And so the spectra that are produced and matched with observations are done in that way. There's no theory that predicts what fraction of the emission from the disk comes from the corona, what fraction goes into jets. It's patching together, the models patch together the Shakura-Tsarnaev model, which just assumes the transport is a viscosity, then calculates a spectrum. A lot of their theoretical work goes into understanding what that transport is, but is it really a viscosity, and is it really small scale? What's missing from present disk modeling is that the spectra ubiquitously modeled with this Shakura-Tsarnaev transport. The simulations often focused on local transport, but all of these non-local quantities. And as I say, little feedback, I think, between decades of the simulation and improved versions of this mean field accretion disk theory. And so as a challenge, a next generation theory should really explain how the disk, corona, and jet contributions arise in their respective proportions and capture the physics of transport beyond a viscous assumption, explain origin of the field, and remain practical. These are kind of grand challenges. Now, why? So, and more explicitly, if we now unpack what is done for the transport and accretion disk modeling, it highlights what's missing. So, accretion disk transport is accomplished by a stress, and you can see that the contributions to the transport from this stress, when you write down the equations in a mean field theory, break the equations into fluctuations plus mean, and you keep large scale and small scale contributions, you end up with all of these different terms. There are essentially 8 terms, 4 for radial transport and 4 for vertical transport that go into the angular momentum transport. And the Shakura-Tsarnaev model effectively just keeps the radial contributions and doesn't distinguish between magnetic and kinetic contributions, and puts this thing into a viscosity. But as you can see, there are large-scale transport terms as well that are typically always ignored. So in the models that observers use, this is completely ignored, the whole vertical transport generally. And this one is the accretion itself. But this is the only real transport contribution and it's modeled as a viscosity. So this just highlights that there's opportunities within the framework, in some sense, of mean field theory to expand to include large-scale transport in addition to what's approximated as a viscosity. And also there's a question of whether this really is a viscosity and whether that's the right paradigm. So for what we've learned from the simulations. Now, a further grand challenge in comparing theory to observations and to show how far away from understanding accretion disks we actually are is this comparison. So in stellar evolution, we have the HR diagram, which allows us to understand the luminosity and temperature evolution of stars of all different masses through their main sequence lifetime all the way through to their end states. We have nothing with accretion disks. We really don't, the pie in the sky would be to have a similar diagram for accretion disks. We don't quite even know what the right variables would be for that analog, but one might be luminosity versus X-ray hardness. And in the microquasars, which is a class of black hole accretion disks, around stellar mass, tens of stellar mass sized black holes. You watch them evolve through various states, and they incur a path through the luminosity and hardness diagram that's somewhat understood, and there are paradigms to understand each stage in this diagram. So something like that, because disks have a range of temperatures, unlike stars, which have a surface temperature and a characteristic luminosity, there might be a different kind of a diagram that characterizes the entire population of accretion disks of something of the sort. But it's way down the road, and that just gives a perspective on the accretion disks. Now, is nonlinear, so transport studies of much of the MRI transport have focused on shearing boxes and understanding the saturated state of the instability. And I'm going to argue that there's evidence that, so as I say, the modelers treat the result of the MRI instability as being basically a viscous transport. When observers go to meetings on accretion disks expecting to learn something that they can take away and put in their models, it's often the case that they come away frustrated. They see lots of turbulent simulations and such, but at the end of the day, they go back to their computers and put in the turbulent viscosity for the angular momentum transport. Now, so there are a number of clues that the transport is not actually, from the simulation, is not actually like a turbulent viscosity. And one of them is sort of an early one. This is a paper by Pessa et al., but if you look at the turbulent MHD stress as a function of the shear, so often people study the simulations with a fixed Keplerian shear because that's the most natural value for what you expect in nature. But if you vary the shear and then you look at the turbulent stress and you compare the predicted viscous model, that would be this solid line. It intersects the Keplerian value here, but if you do simulations with different amounts of shear, the data from simulations does not fit on a curve that is a straight line. It fits on this curve. So that's a very clear indication that it's not strictly a viscosity. And in fact, it was identified in the Abramowitz et al. That it's actually the transport goes as the shear to vorticity ratio. Q is the parameter, omega goes as r to the minus q. The shear, so omega is the angular velocity, and r is the radius or position. So this q over 2 to the minus q is the ratio of the shear to vorticity, and that's what this stress depends on. It's not well understood why that scaling is there. In general, there are other indicators. The stress, if you calculate the stress, so nonlinear proportion of shear, also you see that in these boxes there are large-scale dynamo cycles which correlate with the stress. So the large-scale field is playing a role. I'll unpack this a little bit more. There are if you calculate the stress spectra from simulations, you find that the largest scales, or the system scales of the box, dominate the stresses. And so if you make the boxes larger and the stresses still approach the box scale, the dominant stresses are approaching the box scale, then how large? Then it's suggestive that you're not finding the scale in increasing the size of the box where the stress is dominant if it were local. So that's another clue. And of course, and then there's also a characteristic result that the large-scale fields in MRI simulations, as I'll show, actually arrive before the saturated nonlinear state of the MRI and grow directly as a mode of the instability from the beginning of the simulations. The overall picture is that it's getting away from the viscosity. So this is just showing that cumulative Maxwell stress is dominated by the first few modes in a characteristic box. The details may not be so important here, but the main point, that's the sort of takeaway message, that if you calculate the stress spectra, this particular simulation was isothermal stratified, a YZ periodic box, 4 by 4 by 8. And that's great. And if you look in a stratified box, you find that the stress from the large-scale field, as you approach the top of the box, becomes dominant. So as you go sort of towards the corona, you're getting large-scale structures that are dominating the stress. And of course, in nature, we see the corona and jets and such. And so that's also another example. And the one final point on this part of the talk is that system scale dynamos sort of precede MRI turbulence in unstable systems. So this is an interesting result that the planar average mean fields, and we've done this for vertical or horizontal, actually grow before the mode-mode coupling leads to the turbulence. These large-scale fields are averaged in the nonlinear state, but I'll show you what I mean in a plot right here. So if you look at this is from simulations by Fatima Ibrahimi. We look, and we also did an analytic calculation of this, but this is looking at the MRI onset in a shearing box at very early times in the very early growth phase. Now, this is a phase that you wouldn't see in nature. The systems would already evolve to their turbulent states. But it's interesting to note that the spectra, if you look at the magnetic field, it's actually growing on, so there's a dominant growing MRI mode here. But then here, the field is growing on a large scale before it's saturating on these small scales. So the large scale field is actually growing. These are very early times in the simulation. Tens, within a few tens of orbits. So these are up to these few orbit timescales, and then by about 5 orbits here, but then we've also watched what happens around tens of orbits, it starts to all saturate. But you see that there's power on low wave numbers before the nonlinear mode-mode coupling, and we've modeled this with a kind of EMF mean field approach without worrying about the alpha and beta and helicity coefficients. Just take the EMF, use a mean field, and stick with the EMF in the mean field theory, and you can capture the evolution of this growth at early times well. Turns out that at saturated times, you can also use the mean field approach to capture the growth, but the evolution of different terms in the evolution equation using a mean field theory does capture that early time growth. So that's just a point that if you remember that the large scale field, if it's already growing in the box early times, it doesn't depend on the existence of the saturated turbulence to sustain the large scale field. It's growing off of fluctuations that are seeding the MRI in the very beginning. So the EMF is coming from those initial fluctuations, and the large scale field is already growing off of those. So that's therefore there's also, so the dynamo, for example, that Amitava was talking about depended on sort of there being a saturated turbulence, and he was using the fact that the MRI saturates, it's magnetically dominated, that the MRI saturates with the turbulent fluctuations being magnetically dominated, but but this doesn't depend, the actual growth of the mean field in the simulations doesn't depend that you get to that state before the actual large-scale field is growing. So there's a lot to unpack about the large-scale field and how it grows in these simulations. But this is just another indication that large-scale stuff is important. So just before I move on to the other topic, just as a general point, simulations indicate significant non-viscous, non-local large-scale transport, I would say. And there are different pieces of this. So if you look at local simulations, just kind of summary, the energy and the power in the disk dominated by the domain scale, the role of the large-scale stresses in the boxes, stress spectra dominated at the large scale, and the fact that there's a dynamo, that large-scale dynamo in the box, planar average, that actually precedes the turbulence. And then global simulations also giving similar messages. The large-scale power spectra dominated by the domain scale. Stress and torque in this particular simulation, which is interesting, they take a large-scale field, advect it and find the stress and torque here is dominated by the BR, B phi in the corona. However, these sort of highlight the subtlety of starting with different initial conditions. If you start with a large-scale field in your system and advect it, then lots of the action goes on in the corona, not because it was driven by a dynamo in the disk below, but because it was part of the connected to the initial conditions, which is also a challenge for the global disk simulation. Yeah, okay. Now, so this is one overall theme. This diagram was shown before, and I think in the next generation of accretion theory, this is important. But now, so that's one theme of connecting theory to observations, the need to understand large-scale transport when simulations often are focusing on the small-scale transport and not necessarily producing output that's directly useful for practical observational modeling. That's one point. The other is that I have a very strong student, Hongse Zhou, and we were thinking about the fact that often when you apply mean field theories, either accretion disk or dynamo theory to real physical systems, that in theorists, we often make the approximation that there's infinite scale separation between large and small scale. But actually, there's really only mesoscale separation at best in many of these systems. The sun, galaxy, and accretion disks, the largest scales in the system aren't that much larger than the turbulence. Maybe they're 10, 20 times larger, but they're not, infinitely larger. So the correspondence between ensemble averages and spatial averages, exact correspondence, requires very large scale separation. That's not always the case. Can we quantify that? What implications does that have? So we went on an effort to start to do that, and the whole issue is Reynolds rules in the averaging procedure. We relax the Reynolds rules and calculate correction terms to the Reynolds rules when there's not exact scale separation. And so the usual theory for, say, a dynamo EMF is that you write down the magnetic induction equation, you end up with a mean field equation with an EMF. There's an alpha and beta coefficients. But to derive these equations in this form, the Reynolds rules of that sort are used. If you have finite scale separation, then you need to correct these. And so we use the filtering average procedure, this kind of Germano approach, but we're using it not for the inertial range, but for the mean field itself. So with a specific choice of kernel, one can then you can then pick an averaging scale, and then as a function of the averaging scale, compute averages, and then compute fluctuations, and then averages of fluctuations as perturbative corrections when the scale separation is small-ish, but not infinitely. When there's some scale separation, but it's not infinitely widely separated. So this is so if the kernel is a Gaussian, which is most useful, that's what we do. But we pick our scale KL as a value, which is so basically So it should be noted that when you take averages of kernels and then you think also about averaging over boxes, you start to see that there's also some pathologies with the types with averaging over boxes. For example, if you pick a kernel, if you take a box average, the kernel is actually like a step function. The Fourier transform of that is a sinc function, which has non-monotonic in K and also has modes that with large K that contribute more than small k. It vanishes at certain modes, and so some modes are completely absent that would not be absent in a realistic system. If you imagine averaging over a section of a galaxy, those modes would contribute if your average was somewhat intermediate over the overall scale of the galaxy. They don't contribute. So this is there's a subtlety in the physically appropriate averaging. But when we go through this procedure, perturbative formal perturbative calculation, we end up with corrections to the Reynolds rules that depend on expanding the kernel. The kernel can be expanded. So first order when the scale separation is finite but large-ish, there are these corrections that emerge. You can propagate these corrections, and the corrections depend on the ratio of the averaging scale to the large-scale variation of the mean quantity. And depending on the kernel, the power expansion here is different. For a Gaussian, this is 2. But when you propagate these corrections through the theory, you can write down new mean field theory, and those corrections have to be included. And we've solved a couple cases and tried to quantify the effect of these. Okay. Now the final thing, which I don't need to go into the detail, is that in addition, so that's corrections to the mean field equations by finite scale averaging. It's even more directly interesting is that you can use the same formalism, this finite scale averaging and the correction to the Reynolds rules, to think about the precision of your mean field theory. So in general, if you think of the mean field theory as a statistical theory, if you think of statistical mechanics, when you have an ensemble average, if usually members of the ensemble is so large that you don't have to worry about the precision of the theory. But in the case of mean field electrodynamics or applications to realistic systems, the ensembles are not that large. There's scale separation. The systems are not entirely ergodic. So your theory has a finite precision to it, and you can quantify the precision of your mean field theory, and you find that if you go after observations with a theory whose precision is crude, and you're trying to explain little wiggles in the theory, it's a pointless exercise because the theory cannot explain those little wiggles. It doesn't have the fidelity to do so. So we quantified all that with 2 types of errors, an intrinsic error in the coefficients themselves, and then a filtering error that relates to what you actually calculate versus what is measured in, for example, Faraday rotation of a galaxy. What's measured is the filtering of the actual field through the measuring kernel. What you supply is a mean field theory, which you can then put the measuring kernel. The 2 are different. There's a finite error that you can calculate, and that's the filtering precision error. And finally, the point is, these 2 errors depend differently on the scale separation. The filtering error is reduced the smaller you make so if your large scale over your averaging scale is increased, then you get that error is increased. The intrinsic error goes the opposite way with the ratio of the large scale to the averaging scale. And as such, you can optimize these to get an optimal scale where the precision of your mean field theory is optimized. And that's the best mean field theory you can do for a given system. And that gives you a principle as to what scale you should be averaging over if you want the best fidelity for matching to an observation. And this is an example of minimizing that error. For the galactic dynamo, there is an optimal averaging scale that we found, which is a characteristic here. In any case, that's it. So the 2 themes of the talk, there's much need to use lessons learned from accretion, simulations to prove practical applications to the theory, and then when you use mean field theories in practice, you have to worry about their actual intrinsic precision. I'll say just one point is that this is of direct relevance when you think about observations in one other sense. When you look at X-ray measurements of accretion disks around microquasars, the observations are averaged over kiloseconds, many, many times the orbit timescale and the turbulent timescales of the systems themselves. When you measure observations of protoplanetary disks, you measure observations over timescales much less than a year. So you're sampling the system in a snapshot in the one case, where you're sampling the system and you're averaging over many, many in the other case. So even the comparison of what the observations are giving you, how you compare that to the mean field is really ultimately important to make sure that you're comparing apples to apples. Okay, sorry.
Okay, we can take a couple questions. Let's, Axel, why don't you come up? Axel? There you are. And why don't you give him your microphone and you can, so do we have any questions? Yes, go ahead. You can speak into this mic. Sorry, 1 second for the transition.
Eric, that's very interesting about the perturbed mean field theory. Have you looked at energy transport and transport of quadratic invariance between the large and small scales in this theory?
Not yet. So
this is his,
not yet. Not yet. It's we really just set up.
You have it there, yeah, you can just put it in this one.
Considered the simple implication for a mean field dynamo in.
Did you plug it into the
Oh,
one that it was
no, I
in?
didn't.
This precision error, but that's something that it would be very interesting. There's a whole list of things that might be interesting to see how they're different.
Yeah.
Yeah, that's a good one among them. Yeah.
Thanks.
Other questions? Yeah.
Concerning the scale separation problem, we played recently the game. We took the Taylor instability. We are looking for the M1 mode, which there's nearly no scale separation. But then we played the mean field game, and you get your alpha and your beta effect, and it fulfills perfectly even the Koenig-Seehofer relations between EMF and current helicity. It worked surprisingly well. It's a new journal of physics paper. Even if you have M0 and M1, it works perfectly in this particular case.
Interesting. Okay, that's a good word. Yeah, it's the case that interestingly different galactic dynamo models along the same lines. We found that in some cases the correction terms did not actually matter. So there's a certain there's understanding when they're important and when they're not. It's a system dependent situation, definitely. You have.
All right.
Do I have my computer?
What do you look for? Oh, you want your computer?
Yeah.
Thanks. All right, let's thank him again. And our next speaker is Axel Brandenburg, who's going to be talking about the turbulent chiral magnetic cascade in the early universe.
Thank you, Sarah. Now I'm moving to the entire universe, and I will be talking about first some observational limits that cover the magnetic field on scales beyond that of galaxy clusters, throughout the entire universe, that is. And so any source of such magnetic fields is most likely not of astrophysical origin, but primordial. And that means it is generated at the early times of the young universe. Particularly during the time of the electroweak phase transition, at an age of 10 to the minus 11 seconds, there is possibilities of generating strong magnetic fields that would then be subject to turbulent decay. On the other hand, and that will be one of the main topics of this talk here, during the electroweak phase transition, we are working with the weak force. And the weak force among the four basic forces is the force that is actually violating parity invariance. So mirror symmetry will be broken. And that leads to the possibility of generating helicity throughout the entire universe. So to set the stage here, this is a plot which shows the entire expansion history of the universe, starting with the Big Bang, the inflation at a time of 10 to the minus 32 seconds, and very shortly after that, in some sense, 10 to the minus 11 seconds, the electroweak phase transition. This time is the time where we see, at the moment, the only evidence of physics of the early universe in terms of the cosmic microwave background radiation, and that is already at a time of 400,000 years. Whenever I talk about magnetic field strengths, and I mentioned earlier 10 to the minus 15 Gauss, that applies to the present time and has therefore been rescaled already to the expanded universe. And so that is to be taken into account here. Keep in mind. Now, the observational lower limits are based on the non-observation of secondary photons that you would expect from blazar photons, TeV blazar photons, that would interact with the photons from the extragalactic background light. And that can lead to a pair creation. Positons and electrons, they would recombine again and would produce a shower of secondary photons that one would and should observe. And it's based on the non-observation of this that one argues that the reason why you don't have the recombination anymore is because of the presence of a magnetic field that leads to the divergence of the positron and electron pairs. And so this is, meanwhile, a relatively accepted situation, which leads to this lower limit. And here's a plot from the paper by Neronov et al. In terms of the magnetic field strength in Gauss at the present time versus the length scale on which one observes. So large length scales are on the right. On the large length scales, you have sensibility to a lower magnetic field strength, whereas on smaller scales, only to the stronger field. So you can't pull down the observational lower limit so much. So everything that is in the white area is then still allowed, whereas magnetic field strengths lower than that would not be compatible with the non-observation of the secondary photons. And so this lower limit is a limit then that limits the product of the magnetic field strength squared times the length scale, which I will associate with the correlation length. Up here we are at present-day astrophysical mechanisms where we have galactic magnetic fields on the scales of 100 kiloparsecs or 10 kiloparsecs, and galaxy clusters on the scales of a megaparsec. So those are the present magnetic field strengths, and we were talking about magnetic field strengths that are between clusters of galaxies, and we are now expecting that those magnetic fields must lie somewhere in this range here. So now let's talk about some early work that has led to the concept of talking about turbulence in this context. When I was at Nordita in the 1990s, I was surrounded by these high-energy physicists, and they were talking about magnetic fields that were produced at the electroweak phase transition, and they were puzzled by the fact that since the time of this generation is 10 to the minus 11 seconds, if you multiply this now with the speed of light to get the horizon scale, then of, or to get the so with a horizon scale, if you multiply this by the speed of light, you get a horizon scale of approximately 0.3 seconds. The speed of light is 3 times 10 to the 10 seconds. And so that means the magnetic field would be of an extremely small scale, and therefore likely to be of no astrophysical relevance whatsoever. And that was the situation that I was confronted with, and then I was thinking, of course, of the important work of Anik in the 1970s here in Boulder, that, of course, magnetic fields, especially in the presence of helicity, would undergo inverse cascading. And the people in the high-energy community had never heard about that. Now, of course, they do know about this. So this is this early work of 1996, with Kari Enquist and Paul Olsen, both in Copenhagen at the time. And so we are then talking about an evolution of a plasma that is at the time not really yet a usual plasma. It is called a quark-gluon plasma, but it does have high electric conductivity. And so in that sense, we can use the standard MHD equations. Of course, the universe is expanding. That can be taken into account. That was found, first of all, in our paper here, that you can introduce rescaled variables so that the entire expansion terms can be removed. And that means that you have to work with a time that is called the conformal time that is commonly used in astrophysics nowadays, or in cosmology. The plots that I showed here on the left, this was an early work based on shell models. And so what we see here is energy as a function of wave number. Here at the early time, so you have an initial condition of a random magnetic field, and then later on the magnetic field propagates to lower and lower wave numbers based on inverse cascading. But that was a shell model, and so shell models of turbulence are rather imprecise or not secure. And so there has been a lot of work done on the inverse turbulent decay, and in particular the inverse cascading of that. And so it turns out that once you have turbulent decay, this turbulent decay can often be self-similar in the sense that if you take the magnetic energy spectrum at the wave number k and time t, and multiply the wave number now by a correlation length psi of m, which is time dependent, then the position is always at the same position, which is the scaled wave number k multiplied by the length scale. So the length scale is increasing, and so at later and later times, the peak that is at smaller k's then will be always at the same position of this, which is at unity of this product here. And so we have therefore captured the entire magnetic spectrum in terms of just a single parametric function, which is a function of one parameter only, namely this product. There could be a change of the amplitude that is then taken into account by a certain exponent of the correlation length. Correlation length is defined in the usual way, also called the integral scale. This is the energy integral over the spectrum. And in order to characterize the nature of turbulent decay, it is useful to introduce instantaneous scaling exponents as the double logarithmic derivatives of energy with time, LNT actually that is, and the same with the correlation length. So it turns out there are various different regimes possible. The usual case of a helical decay leads to an energy exponent of 2/3. So the energy decays with time to the power minus 2/3. I think I forgot a minus sign up here. And the same with the correlation length. The correlation length increases with t to the 2/3. There could be other cases, and I will make comparison with that, where we have a non-helical magnetic field, and then the decay exponents are different, or you can have the hydrodynamic case, and again, the exponents are different. So how can you monitor such a thing given a numerical simulation? Well, the answer is straightforward. You use these instantaneous scaling exponents. So here is shown p as a function of time versus q as a function of time. In the hydrodynamic case, you have an evolution as a function of time that settles on a certain point in this PQ diagram. Whereas in the helical case, you settle on a different line, which is a beta equals 0 line, and that corresponds to the 2/3 scaling. If you see here a little bit faint in the background, there are initial spectra that move then gradually to the left. After rescaling them and multiplying by the correlation lengths, you have a single parametric function, which is this one, for the fully helical decay. So this much as a background to how much we have understood about the decaying turbulence. One of the interesting things is that in all those cases, the magnetic field is dominant over kinetic motions, because the initial condition was driven by the magnetic field. And so in those cases, the exponent of the inertial range turns out to be pretty precisely a k to the minus 2 spectrum, which one may want to call weak turbulence scaling. Note, however, that this is a scaling without an imposed magnetic field. Usually, when the k to the minus 2 spectrum has been found, this was with an imposed magnetic field. But here, the magnetic field is not at all imposed. It's the larger scales of the spectrum that are generated because of inverse cascading. Now, in this case, you see some inverse cascading in the sense that at later times, the energy at high wave numbers decreases, but at low wave numbers, the energy increases. And this even, in this case, with a non-helical magnetic field. So that's the case up here. And I will make comparison with that. It turns actually out that in the cosmological context, this one, and that will be at the end of my talk, this one is only marginally important, and most likely this will be the relevant case for the early universe. So now we come back to the fact that the magnetic field was generated through the electroweak phase transition at the time of 10 to the minus 11 seconds. And so the electroweak force involves mirror symmetry breaking. So what is that? The weak force is the force that is involved if you have the decay, for example, of a neutron. That's one example where it was first time studied. So if you have a neutron decaying, it turns into a proton and produces also an electron and an anti-neutrino, an electron anti-neutrino. Now, it turns out that the electrons can have a handedness, and that is because they have both a momentum and they have a spin. And if the two are aligned, they are called right-handed, and if they are anti-aligned, they are left-handed. Now, in general, especially at moderate energies, like the energies that we are living in our room here, the temperatures are low. But if the temperatures are high and the energies are extremely high compared to the rest mass energy of electrons, then it turns out that the spin or the handedness will be preserved for long times, or even forever, provided this condition is satisfied. So that means that the temperatures have to be typically on the order of more than 10 to the 10 Kelvin. But if you remember from the early plots, the electroweak phase transition time is a temperature of 10 to the 15 Kelvin. So we should be safe in that regard. Okay, so if you now have a pseudoscalar, so handedness, of course, a pseudoscalar, in our system, that must have an effect on the MHD equations. And in fact, it does. And it's actually a well-known effect, not just in cosmology. It actually was known only since about 2010. It is also a well-known effect in condensed matter physics, and is also a well-known effect in the heavy ion colliders. So the important thing is that we have a different number density of the left-handed fermions in general compared to the right-handed fermions. And remember, if we are talking about production of electrons through the decay of a neutron, we have only one handedness, namely the left-handed one. So we have different handednesses. For antimatter, of course, everything changes, and we would have only right-handed antimatter electrons. So what happens now? It interacts with the rest of the MHD equations, and it can lead to an alignment of, in the presence of an ambient magnetic field, of the spin. For right-handed ones, it will be aligned with the magnetic field, and for left-handed ones, it will be anti-aligned. But those different charge carriers can have, would have different signs, different sign of the charge. And so therefore, it will lead to the establishment of an electric current, as is seen from such a plot here. So you see the alignment if you oppose a magnetic field, and the effect that we have is very familiar to all of us who are used to work with mean field electrodynamics. But remember, this one is not mean field electrodynamics, but it's still only analogous. And it does lead to a current that is mathematically analogous to the alpha effect in mean field theory. So this coefficient mu now has to do with the chemical potential of the left-handed electrons. And so this is, the current is proportional to the fine structure constant, alpha EM, and it also involves h bar times c and the temperature of the medium. Okay, so now the full system of equations has to be complemented by an evolution equation also for the chemical potential. And it actually turns out that as you produce magnetic fields, and A is the magnetic vector potential, you are producing magnetic helicity. And as you produce magnetic helicity, as is also known from the alpha effect, you are decreasing the chemical potential, mu. And so this leads to a feedback. And so you cannot get away with arbitrary growth of the magnetic field. It will be quenched eventually once you have used up all of the chemical potential. The coefficient in front of this is a coupling coefficient, and this is lambda, which has this expression. You can see it by adding these two equations, multiplying this by b. You have a conservation law for magnetic helicity or total chirality, which is then the sum of magnetic helicity and the average chemical potential, spatially averaged. And it turns out that it is constraining then essentially the product of b squared times xi, which must then be less than this value mu divided by lambda, this coupling coefficient. So this is a quantity that we have seen from in the very beginning, which is a quantity that is being constrained by the lower observational limit. Here's on the total system now also complemented by the velocity equation and the density equation. So energy in such a system really comes from the initial chemical potential, turns into magnetic energy, which then goes forward into kinetic energy, and that leads to the establishment of a turbulent cascade, and that's what I will be talking about now. Before we can do that, we need to understand what are exactly the parameters here. Our lambda can be combined with mu to give something of the unit of a velocity, and there's another velocity that comes from the chemical potential multiplied by the magnetic diffusivity eta. And now we can have different regimes depending on which of these two velocities are larger. Both of them are smaller than the speed of sound, and they're also larger than the diffusion speed, the magnetic diffusion speed. So it's somewhere in the two regimes. We have two different regimes. And in order now to construct the resulting spectrum from our expectations, I want to make use of what we have learned before, namely that in the magnetically dominated case, we should expect a k to the minus 2 spectrum. And so now with that preparation, we can prepare our spectrum. So let's begin as a function of time. We expect a growth of the magnetic field, and this growth will happen predominantly at a wave number which is equal to mu divided by 2. That's comparable to what we know from alpha effect theory. And so it does lead to the growth of a magnetic field. Eventually, it will reach a point which has to do with the diffusive properties, this coefficient mu relative to eta, when it can no longer continue to grow at the same length scale, and it will grow on larger length scales, and it will establish gradually a k to the minus 2 spectrum. And so based on that, based on this fixed point here, we can establish a spectrum which has this scaling k to the minus 2 multiplied by eta squared and mu to the third power. So the final spectrum looks like this. There should then also be an ultimate saturation which has to do with lambda. So nothing of these length scales have to do with lambda, only the total saturation of the spectrum. And now we compare with simulations. And so here you see a box simulation for one particular case and the development of a spectrum. Here the spectrum grows and then establishes a k to the minus 2 power spectrum. And here is how the turbulence looks like at intermediate times. And gradually, larger and larger scales develop through inverse cascading, and you eventually have something like a Beltrami field. Here are the other different cases. The ratio of V lambda divided by V mu is 700 here, and it's 0.07 here. So the higher that becomes, the more will be this limiting value reduced. And so here we have a growth, and we hardly have an inverse cascading. We have directly a decay with constant magnetic helicity. And so here's a final Beltrami field. So this is now what we have seen here. So we have our conservation law, and it establishes a certain value of this product, and we can constrain it in terms of the actual temperature. And that will be the temperature now, if you want to have it at the present time, in the present universe, which turns out to be 2.5 Kelvin, 2.7 Kelvin. So here's now our result shown in the same plot as before, magnetic field strength versus length scale. And we see that we have an evolution for these fully helical magnetic fields that will have a slope approximately like this. And remember, for the fully helical case, the slope is steeper. And it will lead to the shaded out regime, which is now excluded based on our non-observation of the secondary photons. So the only reason, the only regime that this is allowed is the one where we have initial magnetic field strength that must be somewhere in this range, either up here, which is the upper limit given by Big Bang nuclear synthesis, but it must also be stronger than this. Now the result that we find for the chiral magnetic effect turns out to be and that result you obtain just by dimensional arguments turns out to be on this line. And so it turns out that the chiral magnetic effect does exist, but it would not lead to the explanation of the magnetic fields that we do want to explain. And so we have to have some stronger effects. So that is, can be possible if we have other effects where the length scale of the Hubble horizon, for example, would enter. I don't have enough time to go into those details. There's various ways of observing this. Some observational measurements that of the entire of helicity throughout the entire universe based on this calculation of this pseudoscalar, based on the arrival directions of photons of different energies, which leads to a sign that is on average negative. So that already points to a negative magnetic helicity throughout the entire universe. Another possibility, and that's in the future, is if we can observe gravitational waves. And it turns out that gravitational waves will be driven by the Reynolds, by the Maxwell stress in the early universe. And these gravitational waves can be circularly polarized. So here is shown for positive magnetic helicity in red, for negative magnetic helicity in blue, and the corresponding polarization of gravitational wave spectra are correspondingly negative here and positive here. Okay, so with this, let me then conclude and say that in the early universe, we are dealing with decaying turbulence, so similar decay, but if there is a weak force, then there is the possibility of electromagnetic effect being important, which could lead to a completely left-handed evolution in the entire universe. And there's various ways of determining that in future, and so that will be very exciting to see in the next few years and perhaps decades. Thank you.
Perhaps I missed it in the talk, but do you understand why is there an inverse cascade of magnetic field in your simulations?
Why is the inverse cascade what?
In your simulations, or why is...
Okay, so once you have magnetic helicity, as Anik has already shown, and Uriel Frisch, interactions between different wave numbers in a fully helical case can never be to a larger wave number, to smaller scales. It must always go to smaller wave numbers. And that is because of the realizability condition that constrains the magnetic energy from below. If you have helicity, the magnetic energy cannot be less than a certain value. So it comes from the mathematics of the so-called realizability condition, first realized by Anik and Uriel Frisch in 1975 and 76.
Okay, Anik, did you still have a question? And Nick, can you come up while she's doing that? Thanks. And then after.
Yeah, I was wondering whether your cascade was magnetic energy or magnetic helicity. You didn't show the fluxes.
It is magnetic helicity, and it should be. That's also what you would expect, right?
A more practical question, if I could.
Axel, could you say a few more words about your gravitational-driven scenario?
So these are generated gravitational waves generated at the electroweak phase transition time. They are driven for a certain period of time. We are solving this numerically with a pencil code. It's already part of the public domain pencil code. And there's a paper on that also, which has been published and has been on the archive in July. Something specific you want to know about that? Yeah, so these would be gravitational waves that have a frequency of 10 to the minus 4 hertz, 0.1 millihertz, approximately. Okay, so the gravitational waves can be helical. So there's a simple mathematical example. If you look at the Beltrami field, calculate the stress from that, you can calculate directly the transfers and the cross polarization. And so by having both of these polarizations off phase, phase shifted by 90 degrees, that corresponds to a circular polarization of a particular sign. If you change the helicity, that circular polarization, which has to do with the product of cross polarization and normal polarization, you change also the sign of the polarization. And so that's extremely exciting that we can actually observe that. But it does require that we have to have two separate LISA configurations in space. because we do need to know from which direction any particular part of the gravitational wave actually came. Did it come from this direction or from the opposite direction in order to tell about the sign?
Axel, may I ask you a practical question?
Yes.
When the stars began to make the first light, what would you predict to be the magnetic field strength from your processes?
10 to the minus 15 Gauss on 1 megaparsec length scale.
10 to the minus 15.
Yes.
Probably not too much of a dynamical impact?
Most likely not directly, but of course, people have to do their star formation calculation or the galaxy formation or large-scale structure formation. And so it begins to become a borderline, and especially if it's actually more than that. If you remember the plot here, the possibilities of Big Bang nuclear synthesis can lead to stronger magnetic fields, which would be on the order of nanogauss. So remember, the observation limits are just lower limits, but it could actually go up to a few nanogauss, even at 1 megaparsec length scale. And then the large-scale structure formation people should definitely become worried about that. Right? So just lower observation limits we are talking about here. And remember, all of this is actually standard physics that can be done in the laboratory and is done in the laboratory. And we have a program on this chiromagnetic effect at Nordita starting just next week. So that's why I have to go back. It's a 1-month program on this effect. Anything else while they're setting up their talk?
There it is. Okay, then let's thank Axel again.
Thank you.
Axel, we need your mic. Your mic. We need your mic.
Oh, sorry.
Very much. So pin this right up towards the top. Right in the middle towards the top.
How's that?
Okay, so. Thank you. Our next speaker is Nick Brummel, who's going to be talking about the transport of magnetic fields.
Can you hear me? Okay. Yes, hello. I gave a very general title when I first did this, seems it was so far out, but transport of magnetic fields covers pretty much most of the things I do. But actually today I decided to talk about some very specific parts of it and actually get some new work as best as I possibly could into this talk and actually compare it with some older work. And it actually, by comparing it with older work, we bring in some rotational aspects, which is what this meeting was all about, although most people seem to have completely ignored that. I don't feel so bad about ignoring a little bit myself now at this point. But anyway, so the older work was all the work done with Pascal Garot, who I worked with at UC Santa Cruz, and Toby Wood, who was a postdoc at that time back in England. And all the new work is with a graduate student, Lydia Corre, who's now just graduated, just got her PhD, and is coming here as the George Ellery Hale Fellow, and is going to be local to Boulder, so you'll see lots of her, I hope. She's very good, so I'm glad that she got a great job here. Anyway, all the things I'm interested in are to do with this object. We're back to solar things, scaled down from Axel's universe back to almost back to Earth, but not quite back to Earth. And this idea of we know what the interior rotation rate of the sun looks like. We know that there's a solid body rotating interior. The convection zone, the outer 30% by radius, has a faster equator and a slower pole. And we've named bits of this, the interface between these two differentially rotating region and the non-differentially rotating region. We call that sort of interface the tachocline. And so the big question, or one of the big questions in all this stuff is like, essentially, where does this profile, interior rotational profile, come from? So why is the convection zone differentially rotating? I'm not going to talk about that. But why is the radiative interior in solid body rotation, and why is this transition regime, the tachocline, why does it look the way it does? And of course, all of these have ramifications for dynamo action, so that's one of the things I'm interested in, but we're not going to talk about that today, dynamo action per se. Anyway, there's been a number of approaches to this over the years. You can think purely hydrodynamically, as our friends Jean-Paul Zahn and Ed Spiegel did a bunch of time ago, said that anisotropic turbulence could be a friend here, and they could homogenize angular momentum in the horizontal direction when things are very strongly stably stratified. So there was hydrodynamic ideas, although as you heard from Daniel the other day, that actually shear is often not suppressed by such situations, it's actually enhanced, like there's quasi-Bayanol oscillation sort of ideas. So anyway, so in some senses, thinking using a magnetic field is a lot easier. We all know Ferraro's law, which says that essentially velocity should be constant along magnetic fields. Magnetic field acts as kind of a stiffener to a fluid, and so it's hard to differentially rotate across a field line. So if you put magnetic field lines in things, it tends to homogenize the rotation rate. So, so magnetic fields are very good at making things move in solid body rotation. So that's a key component which seems like it would make our lives easier. And then the question is, well, okay, we saw that the deeper interior was rotating like a solid body, but the outer was differentially rotating. That means you have to keep the magnetic field out of the convection zone. Otherwise, that one would tend to be homogenized in angular momentum too, and it's not. So then the problem has changed from one of homogenization to one of confinement of the magnetic field to a certain region so that it does the homogenization there of angular velocity. So we've switched the problem a little bit to this idea of confinement of magnetic field, and that's a transport problem, and that's the sort of stuff that I'm interested in. This idea was formulated very serendipitously by Douglas Goff and Mike McIntyre. They had this paper in 1998, which I'm sure you're all familiar with, where basically you get all the pieces of the puzzle to fall into place. And it kind of goes a little bit like this, and I'm not going to talk in too great a detail about it, just to give the idea, but if I have my convection zone and it is differentially rotating, we won't say where that comes from, then it'll drive a meridional circulation. That meridional circulation, in the absence of other things, will try and burrow downwards into the interior. This is like rotating the lid of something. The rotational effect of that, a lid will burrow down on a slow time scale when it's stratified. It's on a radiative time scale, a slow radiative time scale when it's stratified. And if there is a fossil magnetic field in the interior, homogenizing the angular velocity there, making it solid body rotation there, then the sort of natural expansion of this field out and the diffusion of this field out can meet the burrowing of this meridional circulation coming in, and these can cause it. You can have a boundary layer which has a balance, and these things can sort of achieve a steady state, a statistically steady state. So this was a very serendipitous solution which had everything. It sort of put the interior in solid body rotation, and it had this tachocline, which you could then the thickness of the tachocline depends on the strength of those meridional circulations and the strength of the magnetic field, for example. So you could make the sort of thinness that you want, but it definitely required the confinement of this magnetic field. So this process is a very slow and laminar process, and that's the key to this piece. It operates on this sort of Eddington-Sweet type time scale, which is very long. But it's slow and laminar. But this is one way of confining a magnetic field, this slow laminar balance. Now, there are also, what about faster processes? That was nothing to do with turbulence. What about turbulence? Can turbulence help us in this respect too? Well, there's been a lot of work over the years about turbulent transport of magnetic fields. Here's just an example from a simulation I was involved in with Steve a long time ago. Not that long, I guess, but some time ago. This is just a quick example. This is a box of compressible convection. The upper half of it is actually convecting. The bottom half of it isn't. So this is what we call overshooting or penetrative convection. If you put in just a layer of horizontal constant-ish magnetic field in this thing, which is that yellow layer you see at the beginning of this little loop, and ask where does it go, well, eventually it all ends up out of the convection zone in the sort of stable interior here. Here's a little plot that shows you that a little easier. Here's the field we're putting in. It's in the y direction, so it's sort of a constant to start with here, by. And you let it evolve, magnetic buoyancy takes it around, it gets tangled up, but after a while, it achieves this self-similar sort of diffusing solution whereby most of this field is peaked down below the convection zone. So it's ejected from the convection zone. And this isn't something we invented. There was been a lot of talk about these things over the years, and it has many different names. Diamagnetic transport, back to Zeldovich in 1957. Yeah, you can characterize this in mean field effects as well. So it popped up as the often ignored off-diagonal components of the alpha tensor in mean field electrodynamics, etc. Sometimes known as gammas. There's talk about geometric and topological aspects of this. So if the statistics of the turbulence has some sort of asymmetry to it, then you can tend to move things in a certain direction just by topological effects. for example, described by Jabrashevsky and Yuferev. Nigel Weiss's flux expulsion, which is the ejection of magnetic field from regions of circular streamlines. These are all many different phenomenological ways of sort of describing the same thing, which is actually just sort of the EMF of this thing. It's like, how do I move magnetic fields around by this term? And there's different pieces of this term can be described in different phenomenological ways. But it's been known that there is these turbulent pumping mechanisms for a long time. So the sort of question I was interested in is, well, one is, we've seen two sort of ways. There's slow laminar ways of confining magnetic fields, and there's turbulent fast ways of confining magnetic fields that we know of, or might be possible. Which of these two things wins? Which of these two things is happening in the sun, or are both of them happening in different places, or something like that? So we're interested in sort of the juxtaposition of these two different type of mechanisms. And so, there's these questions of the slow laminar one, this Goffin-McIntyre one. It's a bit Heath Robinson-ish. It needs lots of this to happen and then that to happen, and therefore these two things come to there. There's a lot of jigsaw puzzle pieces that have to fall into place for the Goffin-McIntyre slow one to happen. And if it does happen, and there was turbulence around, does convection, turbulence, and waves destroy that idea that they had, the laminar idea they had, or does it help? In other words, does it just break this nice laminar balance, because it obviously adds extra nonlinear terms to the sort of linear mechanisms they described? Or could turbulence do this confining on its own anyway, without any of this stuff going on? So there's an interesting question, a couple of questions as to what happens with turbulence in this case. Does it help or hinder? Could it work on its own? Those are the sort of things I was interested in. Lots of people have looked at this over the years. There's a whole bunch of people, including ourselves. Perhaps the easiest one to use as an example is this simulation that was done by Antoine Strugarec, Sacha Bern, and Jean-Paul Zahn, where essentially it was everything bar the kitchen sink. They take the ASH code, a spherical numerical simulation of a solar-like type thing. It has a convection zone, it has a radiative zone. You insert a dipolar magnetic field confined to the radiative zone to start with, and you let this whole thing go. This is fully nonlinear. So this thing, it's rotating, it's fully nonlinear. It looks like the sun in sort of the description of the stratification, the rotation rate, etc. So this is sort of as close as you get. The only thing this one didn't have was a dynamo in the convection zone. It wasn't strongly forced enough to be a dynamo. And it's at whatever parameters you can do certain types of simulations like this. But this one has both the slow and the fast mechanisms involved in this one. So you can ask yourself, well, what happens? Well, here's the dipole magnetic field to start with, and as you can see, this dipole field opens up and disappears into the convection zone and sort of is not confined by any stretch of the imagination here. So even though this one seems to have both slow and fast mechanisms, it doesn't seem to show any obvious signs of confinement. Bit disappointing, you might say. Well, we have some ideas. Then there was a lot of work around that time and after that time which sort of said, well, this Goffin-McIntyre, the slow idea, why didn't it work in that case? And in hindsight, it's fairly obvious, but at the time it was a bit mysterious, but it just comes down to the fact that you have to respect the proper ordering of timescales for this slow mechanism to work. And in particular, this slow Eddington-Sweet timescale, that's a slow timescale, but it has to be faster than viscous time. And if you swap these around, if you let viscous effects be stronger than this sort of Eddington-Sweet type slow rotation effects, you're not going to see those slow rotation effects. It's pretty obvious. But and actually, we describe this by a parameter. You can just take this inequality here and put it in terms of this parameter sigma. I don't know why we decided to call it sigma, just to confuse people with the Prandtl number, I guess. It actually has a Prandtl number in it, so that's specifically confusing. But anyway, this number to respect this ordering should be less than 1. And this is the thing you found, is if you actually look at the sun, the stratification of the sun, the rotation rate of the sun, the Prandtl numbers you find of the sun, you combine them into the parameter. Indeed, it is less than 1 for the lower reaches of the convection zone and the tachyon line. Whereas if you did a numerical simulation, you said, well, I tried to make the stratification the same as solar, I tried to make the rotation rate the same as solar, and then I'll do the best that I can in terms of Prandtl numbers, numerical resolution limits to what I can do in terms of diffusivities, so I'll do the best I can. Well, unfortunately, the sun is 10 to the minus 8, and the best you can do with numerical simulations around the times that these were being done is about 10 to the minus 2. And so that gives you this parameter sigma much larger than 1. So this determining parameter was the wrong way around. So we sort of had a feeling that we knew why those simulations were not getting the slow effect, for sure. And this is where Toby Wood came along and did some very nice work. We essentially sort of did a demonstration of this idea as best we could, but not in a spherical geometry, not self-consistently. What we did was take another of these boxes of penetrating convection where we force it to convex on the top. It has a radiative zone or stable region underneath, therefore there's some overshooting, some penetration between these two regions. And then we said, well, let's do what we need to sort of try and see these ideas. What we'll do is we'll force some differential rotation of this thing. We'll rotate this box, we'll force, but it won't self-consistently generate differential rotation, but we'll force, with a forcing function in the equation, some differential rotation. And then we'll see what happens. That should generate these meridional circulations by this gyroscopic pumping ideas. And then we'll put magnetic field down here in the bottom of the box and see if this Goffin-McIntyre balance sort of happens. And the idea is that it should happen if this parameter is less than 1, and it should not happen if it's greater than 1. And I'm not going to show you all the details of this because it's a whole talk in itself, but just to give you an idea, here's a quick picture of that simulation. It actually started off as a convective field that had burrowed its way down into the radiative zone like it should if there's nothing to stop it. So it started off as a simulation which had burrowed down. You insert magnetic field in the lower half of this thing, and then you see that this statistically stationary state is evolved. So you can see the burrowed field now is getting evacuated from here, and the field remains balanced down here. So that serendipitous solution of this burrowing balancing the field, the diffusion of the field outwards that is here does seem to be achieved if this parameter is less than 1. And I could show you the one that's greater than 1 doesn't happen. You have to take my word for it for this one. And in this case, we did a number of calculations just to show that it wasn't, that this, to also prove that this was this slow mechanism. This is a moderately turbulent calculation, so this does have convection and waves in it. So both slow and fast mechanisms are available here. But we think this is the slow because we'd expect the slow to not be able to do this where at sort of polar regions. So this particular one sort of said, well, what was it like near the pole? We wouldn't expect the turbulent mechanism to be able to pump sort of vertical streamlines, but this slow mechanism can sort of park these field lines and still keep them down. So here's a polar one, and again, you can get this nice balance between a confined polar field and this sort of burrowing mechanism happening in this one too. So this, actually just what I just want to say right here, these laminar slow mechanisms do seem to work in this very artificial context at least. The next step to do with these things would be to say, well, we should go to spherical geometries because it's only in spherical geometries can we rotate the thing and self-consistently generate the differential rotation and have it all self-consistent in that sense. So that was the next thing to do, and hasn't been done yet, but the idea was then, to go to spherical things, and that's where Lydia came in, Lydia Kerr, the graduate student, and started working on spherical things, and the idea was to work towards that full model, but there were some interesting things along the way before we could get there. So what Lydia did was spherical things, and we did spherical Boussinesq things. Boussinesq is not a terrible approximation for the base of the convection zone, so we started off with that, using the parity code. We did try to make it a little bit more stellar-like by, well, first of all, we do have a convection zone and an overshooting zone, so we have a convection zone and a radiative interior. There is a core cut out of this thing, so we don't have to do the center. But to make it a little bit more stellar, we have fixed flux inner boundary condition and fixed temperature outer boundary conditions. This is quite a common thing to do for lots of people that do more stellar-like convection experiments. And there's weak compressor. The Boussinesq formulation here is that of Spiegel and Veronis, which allows adiabatic compression as you go down. So there's an adiabatic term, an adiabatic gradient term in the equations. And then what Lydia did in the build-up towards the fully self-consistent thing First of all, we just examined convection in a non-rotating spherical shell. There's some very interesting results on that. There's a paper out on that. I'll tell you the reference if you're interested. Weird things like stable regions can appear. Then Lydia examined overshooting, so not pure convection, convection with a radiative zone below, overshooting. And there's all kinds of interesting results about the dependence of overshooting on the parameters. And then the idea was to say, okay, now we have a convection zone with overshooting and a radiative zone. Let's stick, as Antoine Strugarek and Sacha Brun and Jean-Paul Zahn did before, let's stick a dipole field in the interior and see if it gets confined. So this one is not rotating, so there's no slow mechanism. This is just examining, does the fast mechanism, does turbulent transport work to confine a magnetic field on its own? Okay. Here's the sort of parameters. This is Lydia's chapter 3 of a thing. We're writing it up as a paper right now. The parameters we used are, well, Prandtl number 0.1, which is low, but not as low as solar. But like I said, this is one of the limiting things that happens in these simulations right now. This is a and it has an initial magnetic field with a certain strength, so things are scaled with the initial strength. So there's something which measures how strong that initial field is. It's a dipole. It's a confined dipole in this case. It's not very strong, so the feedback on the flows is not great, so it's almost a sort of kinematic type simulation. It's not a very dynamic in the importance of the Lorentz force sense. And then there's some parameters here which define how stiff the radiative interior is compared to the convection zone, and it's moderately stiff. It's not a brick wall that the convection runs into. And it has quite a strong interface that it hits when it meets there. So it quite suddenly goes for something that's convecting to something which is fairly stiff, which is pretty typical of these sort of calculations. And then what we did was said, well, with these set parameters, we varied the Rayleigh number and we varied the magnetic Prandtl number to see how these things happen. Really? I've been speaking for 18 minutes. That's what it says right there.
It's a 20 minutes.
Oh, okay. He says 5 minutes.
Yeah, 5 minutes to learn.
Oh, okay, I get you. All right. Good, it's all right. We don't have much to go anyway, it's fine. Two things that result from the simulations. Actually, I was quite surprised that I actually we can get a dynamo in some of these simulations, or Lydia can get a dynamo in these simulations, not me, for certain parameters, and some of them are non-dynamos. So we have two sort of classes of results here, which some of them are dynamos and some are not. Let's look at the non-dynamos to start with. Well, first of all, you can see they're not dynamos because we start with some initial field and it just decays. Here's a typical simulation. You can see that there are motions in the convection zone and a little bit of penetration and overshooting down here. But the field looks weak here because it's taken some time and it's already decaying. So it's definitely not a dynamo, this case. What happens to that dipole field? Well, here's the evolution of that dipole field. And yes, disappointingly, the dipole field is not confined in the simulation, right? You can see that the field lines open up, and there's a diffusion of these things outwards. The field decays. You can see the field is decaying here as well. This is the azimuthal field. But we can look at that in a little bit more detail. Change. Here we go. This is the well. What do we mean by what would we hope for in a confined state? Well, we would hope that the dipole component that we had sort of remained in the interior, remained in the radiative zone. And what do we mean by remained? Well, if there weren't convection motions there, this would just be a diffusive problem. And what is the diffusive solution? Well, here we've plotted against radius the strength of the dipole component against radius. And the blue line is what would happen. Sorry, the red line is what would happen in the purely diffusive case. And the blue line is what is actually happening in the simulation for the dipole component. And as you can see, they start off much the same, but as time goes on, 1, 2, 3 here, it still diffuses away. And actually, interestingly, the blue line, which is the simulation, decays faster than the purely diffusive solution. So this is indicative that, what is the convection doing? It's not doing what we wanted. It's not confining. In fact, it's doing the opposite. It's unconfining faster than we hoped. So there's actually a turbulent diffusion of this thing. And you can prove that. You can build a very simple model which has, instead of a constant diffusivity, you add an extra little bit of turbulent diffusivity by this tanh function, so it has stronger diffusion in the convection zone. And if you make this diffusion in the convection zone, solve a purely diffusive problem with this diffusivity profile, with the diffusion being 5 times stronger in the convection zone, then you can actually match the profiles that we got out of the simulation very closely. So it's very clearly a turbulent diffusivity. Okay, so that was the non-dynamo cases that we have. So those were the lower Prandtl numbers, which is more solar. On the other hand, then they're less solar in the sense that the real sun does have a dynamo in the convection zone. So maybe we want to do something with dynamos. To get a dynamo, we have to go to a higher magnetic Prandtl number, where the critical Rayleigh number for dynamo action is a little lower. So this is a less realistic in terms of magnetic Prandtl number. On the other hand, that's the only way we can get a dynamo. So we did that, and you can see here that for this magnetic Prandtl number, 10 to the 6, Rayleigh number 10 to the 6 is not a dynamo, but 10 to the 7 and 10 to the 8 are. So we can do that. What does it look like? It kind of looks like this. Now you can see similar sort of stuff going on in the velocities, but now you actually see scales of the magnetic field which are smaller than the velocity scale. So this is a small scale dynamo. There's no rotation here, nothing to break symmetry, so we wouldn't expect large scale dynamo action. But there's small scale dynamo in the sense that magnetic fields are created at the velocity scale and smaller. And so the question of confinement, what happens to our dipole field? Here's an early time, here's a later time. Well, you can see that the nature of the solution is very different. It does look like the dipole, this is a fairly early time, so you don't see it very clearly, but the dipole is still opening up, it's getting dragged into the convection zone, but now it's getting very strongly tangled in the convection zone, and the parameters are such that this is actually, it can amplify a magnetic field sufficiently against diffusion to make it a dynamo. You can see that here in sort of measurements of the magnetic energy versus time. Here's the total magnetic energy increasing. It's a dynamo. This is for 10 to the 7. This is for 10 to the 8. If you look at what happens to the dipole component, well, you see the same things you saw before. The dipole component is actually diffusing faster. This dotted line, this dashed line, is the diffusive decay rate you'd expect. But the dipole component is actually decreasing faster than that, so there's still turbulent diffusion. But then at some point, the level gets so low that the triadic interactions of the dynamo component are actually creating some component of the dipole. So there's some amplification of dipole due to the small-scale interactions in the convection zone. So this confuses issues a little bit. If you set up what happens to confinement, let's see if this one's working. Yeah. If you have, this is again a plot of against radius of the dipole well, it's a number of things, but one of them is the total magnetic energy, which is the solid line. The dashed line is the dipole component, and the dotted line is the diffusive, what you would expect from a diffusive solution. And again, you can see they start similarly, but as time goes on in this direction, well, if you look down here deep in the radiative zone, things are decaying faster than diffusive as before. So here's the dipole component is much lower than you would expect from a purely diffusive solution. But things are a bit confused now, because if you look at the total magnetic energy, then the convection zone is, by dynamo action, generating magnetic energy. And so there's this plateau of magnetic energy in the convection zone, which then, and the overshoot zone, which then decays towards the interior. So now there's this, what is happening down here is a little bit confused by the fact that we're generating both magnetic energy on all scales, including the dipole, and there's some sort of diffusion of the energy created in the convection zone back into the radiative interior. So in terms of what happens, this is a bit confusing, because now these are plots of both the kinetic energy and the total kinetic energy, which is the solid line, and the dipole, and the total magnetic energy, which is the dashed line. And the purple ones are Rayleigh number 10 to the 8, and the blue ones are Rayleigh number 10 to the 7. And you can see that for Rayleigh number 10 to the 8, getting more realistic, the magnetic energy is getting much closer towards equipartition with the kinetic energy. So the magnetic energy here, though, is created in the convection zone and the overshoot zone, then has this tail into the interior, diffusive tail goes in the interior. But as the Rayleigh number increases, this is getting fairly strong, then this tail, the effect of this tail is going to be quite strong in the interior. So that leads us to these final questions, which are my conclusions. Turbulent confinement or turbulent pumping has still not really been found in any sort of global numerical simulations. It wasn't found in Antoine and Sasha's work and Jean Paulin's work. It wasn't found by us. This doesn't mean to say it's never going to work. Maybe it will work. Maybe we need higher Rayleigh numbers. Maybe more turbulent, in other words, maybe smaller Prandtl numbers to make it more realistic, make it more turbulent. This was a Boussinesq calculation. It doesn't have much asymmetry, so topological pumping is not going to work very well. The only asymmetry it has is the fact that it's in a spherical shell and the boundary conditions and the fact we have a convection zone over it. That makes it all a little bit asymmetric, but it's still Boussinesq, so not very asymmetric. So maybe it's not asymmetric enough. Maybe we'd need to go to anelastic compressible to sort of get more stronger turbulent pumping. That's an open question, whether that can possibly happen. The slow mechanisms, well, we have an idea that maybe what's wrong and what could make these work in the global spherical simulations self-consistent, but we haven't done it yet. That's what we're working up to. But then there's the thing we just learned is if we have a small-scale dynamo in the convection zone, maybe there is this sort of diffusive tail of this, which can be quite strong if the Rayleigh numbers are high, so things are getting towards more equipartition. And would would the small-scale stuff then ruin the Goffin-McIntyre scenario, which kind of needs this sort of magnetically evacuated tachocline in order to achieve their balances? It adds extra terms into their model, which could complicate things. So there's still these open questions about I'm sort of back to the original questions that I sort of asked, is what is the role of turbulence in destroying or helping this slow mechanism? And that's as far as we got, and that's all I have to say.
Right, questions? I see you in the back there. Mike.
What kind of magnetic field strengths are you using in your model? Probably model should be dependent on magnetic field strengths, right?
On magnetic?
On magnetic field strengths.
Restraints?
Yeah.
What do you mean by restraints?
Which kind of Gauss? How many?
Strength. Oh, strengths.
Strengths.
Oh, yeah. This is a very weak initial dipole. That
like in Goffin-McIntyre, yeah.
Yeah, the theory suggests that you only need very, very weak magnetic fields in order to homogenize the interior. That's Leon Messel. It's now from way back when. And yes, the thinness of the tachocline is determined by the strength of the magnetic field. But you don't need a very, very strong magnetic field. We're only putting very, very weak fields in.
Yeah,
it's like 10 to the minus 3 Gauss or something.
If you increase the strengths in the radiative envelope, what happens then?
If I increase the strength
in radiative zone.
In the interior?
Yeah.
You mean in the simulation that I was doing?
In simulation, yeah.
Yeah, we haven't done that, so I can't give you a definitive answer. These fields are very kinematic in the sense that the Lorentz force acting back in the momentum equation is very minimal. On the other hand, I would think that a weak field is more likely to be confined than something which is more dynamically active. So I would expect the results to be less what we wanted, less confined. But we haven't done it, so I can't guarantee that. You never quite know what's going to happen.
Other questions?
Just kind of a related question. So your sigma parameter, I think it depended on the Brundt-Weissala frequency?
Yeah.
Was that at the end there? So you're running these models with overshoot in a Boussinesq setup. Right. So what is actually determining the extent of the overshoot region? How do you maintain the stable layer in the Boussinesq setup?
Oh yeah, we give it a background radiative gradient, which is fixed in space and for all time. So the simulation is run as if there is an internal heating.
Okay, and then so does the steepness of the transition between the unstable region and the stable region, does that affect the confinement at all?
Well, we've only done that for one configuration of the overshoot. We did a great investigation of what the effect of the steepness of the transition and the stiffness of the lower layer was on the overshoot. So yeah, if you make it less stiff and you make the a less steep step, then you would get more overshoot for sure. And more overshoot, you think, or deeper overshoot. But on the other hand, it's the strength of the overshoot which is going to do the confining here. So I think it will be dependent on that a little bit, but these are fairly reasonable, sort of moderate parameters. So I don't expect much stronger, much more likely confinement by changing those parameters, to be quite honest. And we haven't done that survey, but I mean, I don't expect it to change very much. You would try and confine it deeper down, but you know, we're not finding any confinement so far, so it doesn't matter whether it's shallow or deep. I mean, the mixing that you get out of the maybe
Yeah, that's the main thing.
One of the things that you find with overshooting and penetration here is you don't find any real penetration. So there's not real strong mixing. There is overshooting, but there's not real strong thermal mixing, for example. So the mixing of these type of simulations is not particularly strong. Maybe it would require compressible and inelastic to change that.
Other questions? Yeah.
I was going to ask, so in the 3D planar, there is a confinement. Is that right? So, if the radius of curvature is large compared to the scale of the forcing, what would be the? You would think that there would be. So, is there what's the physical interpretation?
Yeah, that's right. But those ones are compressible simulations, and these ones are Boussinet. So that's why I was saying maybe there's a topological aspect of it. I mean, there's two things. It's like, yeah. There's an interesting question. Is a dipole thing, which, I mean, it has some tension and it does have some curvature to it, even if you do make the radius of curvature large, is that substantially different something which is guaranteed, you know, infinitely flat? So that's one question. The other is, like I said, these ones don't have much asymmetry, and those other ones that have more asymmetry in them. So maybe there's a topological aspect of pumping that is missing.
Okay, you have one more? Okay, go ahead.
What were the RMs in your box simulations and in the spherical simulations you did? Were they similar or?
That's a good question. They're not very large, for sure. I mean, they're...
Hundreds, 200s, 500s?
Oh, yeah, 100, 200, something like that. Not thousands, for sure. I don't remember exactly what the numbers are.
And same for the box simulation in which it was?
The box simulations were not very super high resolution, so they were not particularly turbulent. And the magnetic Reynolds numbers were just below 1.
Okay, let's thank Nick again.